Moving too fast. No more questions. 16. Oh, we did that, right? Yeah, we did that. Yeah, counting by reference. No question?
So, yeah, I guess this is just another clarification.
Mhm.
Did we ever come up with like a definition for sufficiently large? Because I know you talked about it a little bit.
Right. So it depends on the question. Yeah, sufficiently large. For some specific question, then the line, sufficiently large line, you need to determine that line based on the, the formula you have. The formula you have. Oh yeah. So you may ask me the question, yeah, sometimes, yeah. Let me give you concrete examples, 2 examples. Sufficiently large. Let me just use some space here. Okay, all right. Sufficiently large. Right, yeah. The first example, n minus 100 to 4th power. Okay, yeah. Then the line sufficiently large, you have to pass that 100 line, right? Yeah, okay. And n0, we make n0 100. Okay. The second example, n minus 1 million to 5th power. Okay, so this time, so here, what I mean is, which number sufficiently large you need to determine based on your question. So when you when you see the formula, when you see all the information, then you can make that decision.
So it's highly based on kind of just what the problem is.
Yes, yes. You cannot say in general, right?
Okay.
Yeah. So you have to have some specific questions. Then you can answer that question. All right. Nobody asked question number 20. Number 20, top 5.
Number 20.
Yeah. Yeah, because this is not a,
Honestly, we can go over all of them.
right. Yeah. But you need to give me the minimum number of comparisons. If the more than minimum, if your answer not close to that minimum, then you won't get any point. Okay? You need to get very close to earn some partial credit. Maximum variation, what?
Yeah, like if you have what is the minimum number, we try and solve for the maximum as well, just in case you bring the maximum.
I don't know. Sorry, and you clarify.
On the test,
Yeah.
if it's prepare for if the question were to be reversed. So instead of looking for the minimum,
No.
maximum.
No. Only one. All good, good. Yeah. Minimum, just minimum. Okay. Yeah. Yeah. I understand, some calculus questions, right? So probably minimum, maximum. Yeah, yeah, but here, yeah, only answer, required. Yeah. All right, so here for this question, among top 5, yeah, I like you to connect this question with the minimum of array. Okay, yeah. Finding the minimum of an array. So you remember this question, right? Finding the minimum. Yeah. So this one and then that one, we can put them under same umbrella, same type questions, same umbrella. So what kind of umbrella? So given n elements, so here we change to n elements. Okay, all right. What is the minimum number comparison that you need to find an element that is among top 5? We change this top 5 to top k values. Then this k we can change, right? 1, 2, 3, 4, 5. Okay, yeah. We make this general version. All right. Then when k equals 1, it's the finding the minimum or finding the maximum, right? Top 1. K equals 1. You find the top 1. Top 1, if we treat the smaller minimum as the winner, yeah. So that's the top 1. Now we change that to top 5. See the difference? We change top 1 to top 5. Okay, thinking that way. All right. To get top 1, what is the main idea of your method? Main idea of your algorithm? Do elimination, right? How many elements you need to eliminate to get top 1? And eliminate all of them? N minus 1. You need to eliminate n minus 1 to get top 1. Okay. Now to get top 5, how many you need to eliminate? Think about that. How many you need to eliminate? How many elements you need to eliminate to get top 5? If you make that connection, you're very close. Think in that way. Elimination, another elimination method question. Top 1, top 5, all right? Top 1, top 5. All right. Is it everything you need? Question? Yeah. So you feel better now? We cover so many. 24. Do you know the formula? Do you know this formula? I remember in one of our quiz questions, you have similar formula for this formula, right? Yeah. So you need this formula, then compare how close they are. Can you make connection? Make connection. Here, assume you have this formula. You need this formula. Okay. Yeah. Anyway, find it. Then just one step away to get this question. One simple step away. Then, after you get this formula, number 24, remember we have a chess. You asked me number 6 question. Is this one related to question number 6? And this one, n equals 8. Think about that. These two questions are related. Okay. Yeah. All right. Any more questions? All right. Yeah, we have 30 minutes, so we can cover some material. Yep. 30 minutes. Part B. All right, let me switch to PowerPoint slides. B.1. All right, yeah. The title, variable size reduction. B.1, reduce problem size by half. Every time we reduce the problem size by 1/2. Yeah, one type. All right, so let's look at this question. Count the binary digits. Given a positive decimal integer n, find the number of binary digits in its binary representation. Yeah. This question, pretty easy, yeah. But here, we want to use the recursive algorithm to solve it. So you may apply some special method to find it, but here, we want to solve it mathematically first. Okay, yeah, all right. All right, so let's do analysis. First, we need to be familiar with binary representation. Yeah, so let's write the standard form of binary representation. For n equals, then bits, numbers, B0, B1, B, the most significant one, B sub S, yeah. And each term, we use that coefficient number. The coefficient should be 0 or 1. So it's a bit number, 0 or 1. Then that coefficient number multiplies power of 2. All right. And the most significant bit cannot be 0. All right. So that's all the information we need when we represent binary representation for a given integer n. Okay. All right. Yeah. So we can assume that this b sub s equals 1, the most significant bit. Yeah. All right. So then the answer, if we count the number of binary digits, that's the bits, number of bits, s plus 1. Yeah. Subscript from 0, 1 through s. So s plus 1. Yeah. So it's a simple one. But here, we want to write the answer in terms of n, not s. In terms of n, not s. Okay, yeah. So here, how to find s in terms of n? That's our question. How do we get a recursive formula? So here, we plan to use recursive formula. How to find that recursive formula for, yeah, so here, for n, but we do problem size reduction, recursion in that way. Yeah. All right. So let's, here we need to find that insight, the most important property here. Okay. All right. So let's do transformation on this formula. So when we start with the standard binary representation form. Then we do transformation on it. Now here. What kind of transformation? We need to take advantage of the structure of that expression formula, power of 2. That power of 2 structure, we need to take advantage of it. Okay, yeah. So the most obvious operation here you want to take, division by 2. Division by 2. Okay, division by 2 operation, then the power of 2 will be useful when you take division by 2. Think about that. Power of 2 structure plays an important role when you do division by 2. Okay, yeah. All right, so let's consider the division by 2 operation. Both sides on our standard representation, left-hand side n over 2, but we take integer division. We do not want that fractional part of the quotient. Yeah, just integer division. Yeah. So left-hand side, we use the floor function. Okay. Yeah. So right-hand side, you can see that B0 term is gone. Division by 2, that only contributes to the fractional part. Okay. Yeah. So B0 term is gone. Okay. Yeah. Disappears. Yeah. And all the other remaining terms still there. Still there. Yeah. But the power of 2, the exponent number is reduced by 1. That's the only difference. For all power of 2 terms, the exponent number is reduced by 1 when you do division by 2 operation. But we want to find the number of bits in our representation, right? The number of bits. Now you can see, since if you compare the number of terms in the bottom representation and the number of terms in the upper representation, the only difference is that one term difference, B0 term. B0 term, that's the only difference if you compare the number of terms. So difference is 1. Okay, difference is 1. All right. Now, yeah. When we do division by 2, we remove the least significant bit. B0, the least significant bit. Okay, we remove it. So the number of bits is reduced by 1. Exactly that. One number reduction. Okay? The problem size is reduced by 1/2. Left-hand side, n/2. The problem size is n/2. Flow function. Yeah, flow function. So approximately 1/2. Half size reduction. Okay. Yeah. The recurrence formula, if we use the function bin rec binary recurrence, yeah, this function bin rec of n, yeah, we count the number of bits in binary representation. That's the value for this function. Yeah, left-hand side. So the right-hand side, we call this function recursively, but on the problem size n/2 flow function. Flow function. And what's the difference? So you have the same problem of 2 different sizes. Left-hand side, size n. Right-hand side, size n/2 flow function. Okay. So for these 2 different sizes, the difference is only 1. The function value difference is only 1. Yeah. So we get this recurrence equation. Recurrence equation. The question is, next question, how to solve this equation? We need to solve it. Yeah. All right. Yeah. So it's not easy, but we need to solve it. Okay. Yeah. All right. So here, yeah, let me just do it step by step. Yeah. We try to apply some problem-solving strategies here. Okay. Yeah. All right. First, when you look at this equation, anything special you have noticed? Something? Yeah. So which part in this equation you feel make it difficult, make this equation more difficult? Any part? So when you need to work on it, there is some part you feel hard to handle. Is there any place like that in this equation? Technically, not that easy to handle. Any place like that? Right? How about that flow function? Is that not quite, sticky a little bit? Yeah. So, yeah, because you don't know what time, when do you need to make truncation or not, right? Sometimes you need to do truncation, sometimes you do not need to do truncation. Okay, so that may cause some uncertainty here. Okay, yeah, not quite easy to handle. Right. Then, remember we have some strategy in this situation. When we have different cases, we always focus on the simplest case. When we start, we always start from the simplest case. So can you imagine for some ideal case that could make that equation simpler? Some ideal case, you can make assumption. You can make some broad assumption, brave assumption. Okay, to make that equation as simple as possible. Do you make assumption that n is an even number? Even number, then you don't have that truncation problem. The floor function can be removed. Yeah. So, because we want to make our life easier, so here we make that assumption to make our problem solving easier. Because the harder thing we can delay. Okay. When we start, we want to start with some relatively easier, modest goal. Okay. Yeah. So here we make assumption and even number. Okay. Yeah. All right. Yeah. So here, yeah, when we solve here, let me switch to a closely related question. Yeah. We make A of n the number of additions. How about that? Number of additions. Because when we count the number of bits, so here, every time we need to do one addition plus one. Okay. Yeah. So we use A of n to count number of additions. In that case, our equation becomes A of n equals A of n over 2 floor function plus 1. Okay. And A of 1 equals 1. Yeah. We assume 0 plus 1. Okay. Yeah. Similar equation, but our interpretation slightly different. Okay. Now we do analysis. How to handle the floor function. How to make the floor function part easier for us. Make assumption, right? Yeah. So we know when n even, it will be simpler. Okay, odd, a little harder, right? Odd, little harder. Yeah. So we like to assume n even first. If n even, yeah, the floor function is gone. The floor function is gone. Okay, yeah. But the problem is when we do recursion, we apply it on n over 2 floor function another time, recursion. Now we have the problem for n over 4 this time. Okay, n over 4, that may not be an integer, right? No, it may not be an integer. No. So we need to make another, convenient assumption here. How about we wish n over 2 even this time? Then the floor function is gone. Floor function is gone. Okay, yeah. So think about when we apply recursion all the way down to the bottom, we want to have the floor function disappear everywhere. Floor function disappear everywhere. And that could happen when n is power of 2. Only when n is power of 2, then floor function, we don't need to deal with it. That's the easiest case we can imagine here. The easiest. So when we start, we want to work on the easiest case. That's the one. N is power of 2, easiest. Okay, think about it. If I give you that assumption, n is power of 2, can you find a solution for this equation? So let's find it. Solution. Okay, all right. Now, let n equals 2 to the kth power. Okay, yeah. And k, if we write it in terms of n, log base 2 of n. Okay, okay, yeah. Then let us write the original recurrence equation in a form without floor function. We don't want to see the floor function anymore here. Okay, yeah. So now you replace n by 2 to the k and n over 2, because it's power of 2. So it becomes 2 to the k minus 1. And you don't need floor function here. Okay, all right. Now you get a new recurrence equation. Yeah. How to solve it? The question. How to solve this recurrence relation? Okay, yeah. That's, yeah. It's pretty easy here. So let's do the quick work here. When we work on it, let us apply recursion a few times. Okay, yeah. Next time, every time, yeah. So we, yeah, dot, 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 the last one, a of 2 to the first equals a of 2 to the 0 plus 1. Okay, yeah. Can we find the answer of a to the 2 to the k? No. If we add up all these equations, we can do a lot of cancellations, both sides. Cancellation like this. Yeah. All this kind of diagonal cancellations. Yeah. But at the end, top left corner, this term is left. Bottom right, this term left. But how many equations do you have? Can you count on that number? We need to count the number of equations we have. Can anyone tell me the number of equations we listed here? This whole block, how many equations? Counting by reference. Can you find suitable reference? Counting by reference. Which reference is convenient to use? What reference do you use? Reference object do you use? Each equation. Yeah. All right. Each equation you can associate with superscript. How about that? Each equation, there is a different superscript. How about that? If you look at these superscript, how many superscripts do you have here? You have, okay, you have superscript from 1 through k consecutive numbers, k numbers. So you have k equations. K equations, that means you have k ones, okay? Because each equation you have that one term. So k equations, you have total, adding up all the ones, total, k. But there is another a of 1, that's another one. So you have a of 2 to the k equals k plus 1. So for this special case, you get a solution. But this solution is not in terms of n. So we want to convert it to another expression that must be in terms of n. Okay, yeah. So now we need to switch back to n expressions. A of n equals 1 plus that k, remember our k, log base 2 of n. So we replace k by log base 2 of n. So we get a formula, this time in terms of n. For the solution, special case solution, not the general case solution. Special case when n is power of k, a power of 2. Only your n takes this special form, this answer is correct. If your n is not a power of 2 expression, you cannot use this answer. This answer may not be correct. Okay, all right. So that's our partial solution. How about that? Partial solution, not a full solution, not a complete solution. Complete solution, it should be true for arbitrary n. That's our complete solution. Okay. So our next step, how do we get to the full, complete, final solution? We want to consider arbitrary n number, not just the power of 2. Okay, yeah, here. We need to apply another strategy we used before. Okay,
Like in the coin problem.
queen, not like queen,
It's like a
Wait.
coin problem.
Wait.
right? The weights.
weights,
Like
fake
where
coin,
It's, yeah, fake
Fake
coins
coin.
where it's sort of like the range is going to be.
rain. Let me see. Yeah. Here, the strategy I want to remind you, guess and verify. Guess and verify. All right. So now we move from special solution to our final solution. Okay. Our final solution. There is a gap. There is a gap. Okay. Yeah. But can we make a guess for our final solution? We need to make a guess. Okay. Yeah. All right. So this special solution, we make it as the starting point in our guess. Yeah. Think it out. When you look at that formula, if we directly jump to the final solution for arbitrary n, like that log base 2 of n, that function won't give us integer, right? Log base 2 of n, it's not integer. But when you count number of bits, it must be integer, right? When you count number of bits, it cannot be, log function, it does not return integer value. It does not make sense, right? Yeah. So here's the question. How do you go from non-integer expression, this is a non-integer expression, non-integer expression to integer expression quickly? The easiest way to move from non-integer expression to integer expression. Good, truncation, okay, truncate, yeah. Truncation floor function, yeah, that's the, so we make our guess, okay? When we move to the general case, we make this guess. We take floor function of that log base 2 of n function, okay, yeah. Is that the only way we can do with the floor function? The only way? Yeah. Is there a way, another possible way we take ceiling function? Ceiling of function also allows us to go from non-integer expression to integer expression. Which one we should take? The floor function one or ceiling function one? Can you justify it? Why floor function? Yeah, special case. Special case.
What do you mean?
All
I
right.
think, yeah.
Consider n equals 3. N equals 3. Okay, yeah. N equals 3, when you write a binary representation what is its binary representation?
1, 0. No, wait, that's five, sorry. It's just 1, 1, right?
1, 1.
Binary.
1, 1, 2 bits, right? When you count 2 bits. All right. Now log base 2 of 3. You take a floor function and a ceiling function. Floor function you will get 1. Ceiling function you will get 2. Right? So which one when you do here correct? Yes, 1 plus 1, so you should take the floor function. 1 plus 1. Yeah. So here, when we make a guess, we need to verify it. Okay. But this verification is a simple verification, right? You only check n equals 3. How do you know for arbitrary n it's correct? How do you know when n is 1 million it is correct? How do you verify not just for one special n, for all the possible n's it's correct? How do you know that? How do you prove that? Okay, yeah. Here, I just tell you the way, yeah. Mathematical induction. How to prove it? Mathematical induction. To rigorously prove it. All right. Yeah, this is the rigorous way. Okay. Mathematical induction. Okay. Yeah. All right. So the next step, in order to push it to arbitrary general n case, we need to apply mathematical induction to rigorously prove it. But for this class, at this point, I may skip this one. I skip the mathematical induction proof because later, when we move to Fibonacci numbers, we need to apply mathematical induction another time. So I just combine these two places to one. Now, I can save some time. Okay, so here I do not do the proof here, yeah. But when we move to part C and part D of module 3, we do only one mathematical induction proof for Fibonacci number formula. Okay, you go through the whole procedure, mathematical induction, yeah, at that time. Okay, but not here, not here. All right, so let's